Hey gang, and welcome back to another worksheet solutions walkthrough for the worksheet, reaction practice of ketones and aldehydes part 2, making them harder. Okay gang, so again, a lot of reactions in this wonderful world of ketones and aldehydes where we've delved way deeper in how we can work with these two specific types of functional groups, right? It can get crazy, and if you're coming from the first worksheet, if this was hard, don't worry, it was meant to be hard. But if you can, handle obviously the problems from the first worksheet, but if you can especially handle these ones, of course, if you didn't get them on the first try, that's okay. But if you can look at them and practice them and really understand them and, overcome them, then you're in a really good spot, in my opinion. So this one's a little bit shorter than the last one, but I think the problem quality is a little bit higher, a little bit harder. So we'll just go from top to bottom like we always do. Hopefully you can find the explanations that you're looking for in terms of how the answers were arrived at, and I can help out with that. So let's get started. Okay gang, in part 1, problem 1, we have 2 parts. This is part 1 of 2. We're gonna do the first 4, then we'll do the second 4. So we take a gander at our first 4 problems. So when we look at this right here, so in this particular problem, right, we have to fill in the reagents. We need to tell the story of how we went from this reactant to this product. Now, some key differences, right? You see we have a diol here, and in fact, we only have one alcohol over here, and that alcohol, right, my front's right, plus an enantiomer. So obviously we get an enantiomeric product mixture. We have a deuterium over there, and also, I hope you can see, this is a carbonyl, while that is still an alcohol, and obviously a different type of alcohol. So hopefully what you can maybe see from here is clearly we had some type of oxidation happen, right? I think we oxidized both of these, in fact, and then I think we protected one of these two because we do have symmetry, so it doesn't matter if which one we would protect really, it just matters that we kind of put in one equivalent of protecting stuff. So I think we oxidized, we protected, and then we did a reduction that only affected one of these two alcohols, which then became carbonyls, ketones more specifically, and then I think we deprotected, and that was the whole extent of this problem. So follow me on this, we'll go stepwise. I think the first off the bat, we oxidize these two alcohols to ketones. Now we can do this with PCC or with the sodium dichromate and H2SO4. I'm gonna write PCC because it's fewer letters, and I'm a little lazy, okay? So I think that is what we got. So after that first step, no stereochemistry, right? We have 2 sp2 carbons, we have 2 ketones. Now I think is when we protected. So I think as a second step, we threw in some type of diol, and I'm gonna use our ethylene glycol standard, and I'm gonna use, well, you can write H+, H3O+, whatever. And if you wanna be extra careful, you could even write one equivalent. I'm gonna write one equiv. What that will do, and I'll draw this over here, and it doesn't matter which one it happens on, but this will turn one of the ketones into a diol, okay? So then, as a third step, we can actually reduce this, and you need to use something that has deuterium as a source. That's your source. You need D-, not just hydride, H-. So it's up to you in terms of what you want to use. On the answer sheet, I did use NABD4 with a follow-up of ethanol. Just know you could absolutely use LA. It wouldn't be LAH, right? It would be lithium, aluminum, not H4, like I was about to write. You could use this as well if you're wondering. LiAlD4 with a follow-up of H+ to make sure you get the OH. So you could get that, and then last but not least, right? So after this step, right, D- would come in, it would attack, and then your ethanol would provide an H to quench that negative charge. So that's where we get the enantiomeric mixture from. Whoops. That's where we get, right? Because that is an sp2 carbon, the carbonyl carbon, right, that we had here. So the deuterium doesn't care if it attacks on top or on bottom, it will do so in equal amounts. And then last but not least, we need to recover our ketone. So you just need, you could write H3O+, you could write H2O and H+, whatever you feel comfortable with. That will flip this acetal back to the corresponding carbonyl it came from. And that, my friends, gang, is the first part, the first problem in part 1 of problem 1. Okay, now this reaction moving on. So we see 2 carbonyls and we see the reagents for a Wolff-Kishner, okay? Seems pretty standard. But remember, Wolff-Kishner's only affect aldehydes and ketones. Because what we have here, in fact, we haven't talked about them yet, and they are less reactive. This is an amide. It's not just your regular carbonyl, okay? That's an amide. So I included this just to show you, just to highlight the Wolff-Kishner will only affect aldehydes and ketones. So we're only going to erase this top carbon, carbonyl. This will stay exactly the way it is. So your product looks like this. So it's almost like the Wolff-Kishner didn't work, and that's right, it didn't work on the amide, but it did work on our ketone, okay? That's why I included this problem. Let me make sure I didn't lose any carbons. 1, 2, 3. Yep, okay. So down here, a little bit more of a multi-step problem. So, and I think you can see the PPH3. So you may be thinking Wittig, and you're absolutely right. So in this first problem, we're going to do radical chlorination. So we'll put the chlorine on a primary carbon versus a secondary carbon. That was just a bit ugly, okay? Then we bring in the PPH3. The PPH3, this is step 2, does SN2. So this is kind of going into step 2. I hope you're thinking we will be, so PPH3, we have a positive charge on the phosphorus. The butyl lithium functions just like LDA or T-butoxide. It's just going to be, it's a wickedly strong base. So all these steps, 1 through 3, is just to prepare our yllid. So you can do this if you'd like, or you can have the positive charge here and the lone pair on that carbon. It's up to you, okay? So let me make some room here. So it's this carbon we'll be attaching from, or again, if you want to think of it like this, you can absolutely think of plus charge here, negative up there. And we have this 3-carbon aldehyde. Now I wrote the aldehyde this way on purpose, kind of to throw you off in a way, just to make sure, you know, don't lose any carbons. Don't let me trick you by writing this as a C. Don't shorten your chain on accident, okay? So we know this flow, right? The carbanion is attracted to the carbonyl carbon. This oxygen will bounce and take its electrons to bond to phosphorus, right? We form that 4-membered ring. And remember, we have to check for our, you know, is our yllid, is this carbon off of a conjugated system? The answer is no. So we're going to form either a Z or cis double bond, Z, cis, whatever the terminology that's appropriate applies to, right? So in fact, this will be a cis double bond because we're going to have 1 alkyl group on both sides. So 1, 2, 3, 4. Let me just draw this. 1, 2, 3, 4. Let me draw this a little bit more appropriate, like easier for me to. So 1, 2, 3, 4. This carbon will be bonding to this carbon. So I'll take my dot. I'll draw a line to this new asterisk. And I know that's a chain of 3. So the point being is that we have 1, 2, 3, 4 carbons that lead up to a dot. 1, 2, 3, 4. We know it's going to be a Z or cis double bond, right? Both terms apply here. I double bond from the dot to the asterisk carbon up here. And just make sure that this is one of 1, 2, 3 carbons because it's part of 3 right there, okay? Now, last but not least, we just have a very, enamine formation problem. But it's a little bit different than the ones we've done before. So, or the one on the previous worksheet, I should say. So we know we're going to form a double bond either this way in blue or this way in black. Now remember, the primary goal is that we need to make an E double bond. That helps with our sterics, and if we can favorably lock a big, thing away from the amine that we're going to attach in our enamine, we will do that. So the thing is that we do have a hydrogen available on both positions, and I think you're seeing that this is bulkier than this, and I'm not even circling the whole thing, right? This group alpha to the carbonyl is actually an isobutyl group. So we want to lock this E because the ethyl group, this is a little bit branched. This is just straight line. So what I wanted to highlight was if I want to draw this right here. So there's the ethyl group. I didn't change anything over there, but it's this carbon that's right here, and you see I have my double bond, there's my enamine, then I can actually lock this like this. This branched piece of the isobutyl group is now locked this way. It minimizes any potential sterics that could have been there, between the isobutyl group, the kind of isobutyl substituent, and this, so that's why the double bond goes to the left as opposed to the ethyl group. The ethyl group just isn't the bulky group in this case, it's this right there. Okay gang, that does it for the first part of problem 1. Let's round out problem 1 with part 2. Okay gang, to round out problem 1, second part of that we are shooting, we have 4 more lovely problems to conquer. Okay, so again, we're starting off with another problem where we're given the reactant, we're given the product, and we need to tell the story of how we went from beginning to end. So, clearly you can see another benzene ring appeared out of nowhere, but that's okay, and you're totally allowed to throw that in. I feel like sometimes the fill in the reagent problems can feel weird because you don't know what you're allowed to use. Alright, so, but you can see again we have symmetry, and you can see that we just have one group affected versus 2. So, but as even at thinking before, just diving in, let's think about what's happening at a high level. So you can see that we have 2 carbonyls, one of which remains unaffected. And in terms of the second one, right, we can think of this one being this is the carbon that is now the linkage between these 2 benzene rings. So you can see really just over here, that's just benzene. We can totally grab that off the shelf. We know that's super available, like the shelf of a lab. But what I hope you can think, we will definitely be using this, an AlCl3, right? But that means that this, we can stick this together with a Friedel-Crafts acylation, which means this carbon right here would have to be an acid chloride, okay? So I think now we're maybe getting somewhere. This is a long problem, so thinking backwards kind of helps in a way. So I think what might be helpful, let's just leave this as an aldehyde for right now. That this won't be able to stay this way, and we'll see why. But we would absolutely need this to be an acid chloride to then stick this on, okay? So we can absolutely oxidize this, treat this with SOCl2, and then we'd be good for this Friedel-Crafts acylation. However, right, if we oxidize this, there's a good chance we're going to oxidize this too. So the trick here is using the right protecting group, because when we oxidize stuff, we have an aqueous environment. And that's not going to work with acetals, because aqueous, aqua, means water. So I designed this problem to specifically make you have to use a thioacetal protecting group, okay? So as a first step, what I want to do is we will be using, a very, very similar, and it's because I'm running out of room up top. It's going to be basically like ethylene glycol. It's just going to be with sulfurs now, okay? So as step 1, you have your 2 carbons with your SHs on both ends, your zinc chloride, and some acid. Again, if you have different reagents, please be sure to use those. I just am going off of what I have in the textbook that I use. Okay, so this will, now what I'm going to do is we're going to kind of start back at the beginning. So after this, and you could put one equivalent if you'd like, but if you just don't specify anything, someone would understand you're going to be doing this, okay? So this protecting group is not sensitive to acid, which means now that we've protected that, we have full reign now to oxidize our other aldehyde. And yes, we do need to go all the way to the carboxylic acid. So we will be using the Jones oxidation. We will be using sodium dichromate and H2SO4. So after doing that, this is step 1. Then including step 2, all that does is this right here. If we had an acetal here, it would have been unraveled, and then the recovered aldehyde would have been subsequently oxidized, and that's no good. So now at this point, then we can throw in SOCl2, because now that we include step 3 here, remember SOCl2 in an SN2 fashion replaces your OH right here, and it will make that a chloride. Now we can perform the Friedel-Crafts acylation, right? So that's when you break out the AlCl3, you bring in the extra organic piece, you bring in benzene. That will actually stick these pieces together. Let me redraw this. It'll basically look like our product minus the fact that we still have our protecting group on. Let me draw this real quick. So we have this now. So now all we need to do is deprotect, recover our aldehyde. So yes, I know this is probably the longest of these problems. And again, these reagents, if you have different ones, please make sure to use them. But my book calls for the mercuric chloride, the HgCl2 is the most important part of this. And I'm tossing in water along with calcium carbonate, and I think the this last CH3CN, that nitrile, is just for solvent. But these are the stars of your show right here. Okay? So, long-winded way of saying this is a problem that exposes the fact you have to use a protecting group that's not sensitive to acid. Okay, moving on. Whoops. And not erasing our problems. Okay, so moving on to this problem right here. We need to provide the two reactants. So hopefully now that you've been through the ringer, I'd say, when you see a double bond connecting what looks like two big organic pieces, this should hopefully be tripping your Wittig senses, okay? So when you see a double bond like this, let's evaluate if it's E or Z, because we'll have to, that might dictate which, on which side our yelid has to be. Looking at this double bond, this is the highest priority thing on this side of the double bond, and this is the highest priority thing on the double bond. So gang, what I think you can see here is this double bond, right? You can see the highest priority groups are on different sides. This is an E double bond. So I know I've been saying this up to this point, but finally we have a case where our yelid must come from, it must be off of a conjugated system. So you can see, now that we know this is an E double bond, this side must be the yelid, okay? And I'll draw it like, again, you can draw it multiple ways, but you can see this carbon is included on this right here. This must be the PPH3. Again, you could also draw it like this right here with the charges shown. But again, it's directly off of this conjugated system. It happens to be benzene, it happens to be aromatic, but that's why we end up with the E double bond. And for our carbonyl, that's a little bit simpler. The carbonyl is right here. I'll use an asterisk. So you can see this piece right here has the cyclohexane ring and two carbons. I'll draw it very, very similarly. Maybe not. I have to draw this a little bit higher. I'll do it in blue. So you can see 1, 2, and there's the carbonyl. Okay? So there's the yelid, there's the carbonyl. It happens to be a ketone here. Okay, so moving on to here. So hopefully you're seeing here that we have a cyanohydrin. And the very first thing we see is that we're going to unravel the cyanohydrin and recover. We're going to recover the carbonyl it came from. Sorry, the words are not coming to me in this video, gang. I'm sorry. So after the fact, what this will be doing is we will recover this right here. Because we just have this carbon, that's the carbonyl carbon right there. And then you can see we're going to throw it into imine mode. So we're going to get this carbonyl back, and we're immediately then going to form an imine. So remember, you're going to have your carbonyl carbon just like this, but you're going to have a double bond to a nitrogen, and whoops, and I definitely meant to make this just ET and this be NH2. NH2, it's because it's a primary amine, right? So we form an imine primary, or ammonia gives you the imine. So you get the double bond right there, and then the one alkyl R group happens to be an ethyl here. So this is our imine product here. Okay, last but not least, down here. So you can see right here we have carbonyl, nothing special, just an aldehyde. First step is going to be attack with ethyl Grignard, okay? So we're going to boot that up. I'll do my work over here. So you see we have this over here. And then that's step 1. Step 2 would just be to quench that negative charge, make it OH. And if you're wondering, Joe, yeah, it would form a racemic mixture. You're absolutely right. But it actually doesn't matter, because we're going to oxidize the carbon that was attacked to an aldehyde. Okay? And then after we've done that, it's Baeyer-Villiger oxidation time. And I wanted to include this because remember, even though, and I'll draw this now, we just have an ethyl group over there. Remember, you can't do the Baeyer-Villiger oxidation to the side that has a quaternary carbon. The highest it can go in terms of the migratory aptitudes that we consider is tertiary. So, nothing happens to the left of the carbonyl, but we form our ester off to the right. And you can see we still retain the 2 carbons right here that came from the ethyl Grignard. And if you really wanted to, you could write the ester like that. I included both on the solutions. Okay, gang, that wraps up problem 1. So let's smash a mechanism and crush a synthesis problem and close out this walkthrough. Okay, gang, rolling on into problem 2. You can see we have a mechanism. We're given this transformation and we have to explain with mechanistic arrows how it happened. Now, this is weird because not only do we have a ring right here, but it's like, you know, we have this 5-membered ring, but then we have this little ring up top here. And as crazy as it looks like, because I know it's a lot to digest at first, just stick with me on this. If we almost look backwards, I hope you can see, okay, we're in an acidic environment, and if we were to go backwards, right, you can see carbonyl, 2 alcohols, and then you see that these two oxygens are bonded to this carbon, and I'll explain why it's this one and not this one. This is really just, all we're going to be doing is unraveling an acetal, okay? Hopefully I didn't spell unraveling incorrectly. Anyways, so you see that this is the carbonyl we're dealing with. We see that there's 1 carbon to the left right here, and then there's 1, 2, so 1, 2, 3. There's a 1-3 relationship between those 2 methyl groups and the carbon that is our carbonyl carbon. So I hope you can see is, here's the CH3 to the left, and then 1, 2, 3, okay? So this is the carbon that was our ketone, because if we did it backwards, if we thought this was the carbon that was our ketone, you can see that the carbonyl would be next door to where these 2 methyl groups are, and that's just not what we see in our product. In fact, it's the OHs, right? OH being next door neighbors with the carbon with the 2 methyl groups. So again, that was just to help you digest the problem, but nothing changes. You already know how to do this. The first thing we're going to do is protonate one of these oxygens, right? Because now we need to play the game of protonate everything we want to leave, and then we need to reintroduce water, which will then become our ketone here. So right off the bat, I'm going to use hydronium. Doesn't matter which one you pick, but I'm going to pick off this top carbon first. So this will grab H+. So moving down over here, oxygen. So we have this right here. I'm going to draw it like this, because I'm really just trying to get rid of this just so I can get back to a normal type of structure that's not bicyclic. Okay, so now we have this. So now think about what you need to do. This is usually the part where we reform an oxygen double bond with a carbon, and we boot off one of the alcohols, and that's still what we're going to do. I'm going to reform this right here, and then I'm going to boot these electrons onto that oxygen here, thus breaking the fact that we have kind of like an oxygen over top of the ring. So, a few key things that just happened. Still have these 2 methyl groups here. Now I just have a wedged OH over here, so I hope that's apparent, okay? Wedged OH. I have a double bond here, and I have a plus charge on this oxygen, and since there's a double bond here now, and this is an sp2 carbon, no longer is that methyl group dashed. It's planar. It's just a straight line, okay? So at this point, you can almost think of this as a activated carbonyl, right? Let's bring in our nucleophile, which is water here. So water attacks, electrons kick up onto that oxygen right there. So this is that plus H2O step, which we know is so important when we form acetals. Okay, so now we have a wedged OH, just a single bond there. Still have this right here. We're going to leave that because we're not going to be seeing any stereochemistry there. And then we will see we have the newly introduced oxygen from water, and it has a plus charge. Now remember, we want this to stay and we want this to leave. So this is time for the proton shuffle, right? We want to protonate who we want to get rid of, and we want to deprotonate who we want to keep. So in this step, I'm going to show a water deprotonating the oxygen that will eventually become our ketone, and I'm going to show this oxygen that's currently an ether, gonna protonate it so it's getting ready for that CO bond to break. So in doing this, again, these methyl groups have done nothing the entire time. This wedged OH is just hanging out. I need to actually put an oxygen in here. It has a plus charge. I now just have a regular OH, still have that methyl group. So now this is that really important part where this oxygen rightfully forms what will become the ketone, right? We form a carbonyl, C-double-O bond, and then we boot off this oxygen, which is now a good leaving group because we protonated it. Okay? So after we do that, what I want to do actually is this now breaks our ring. So what we're going to have is 1, 2, 3, 4, 5 carbons in a row, which you can see is what we have up here. 1, 2, 3, 4, and 5. Okay, so we're getting super close. So 5 carbons. You'll see this is 1, that's 2. 1, 2, 3, 4, and 5. So now on 2, I have a double bond to oxygen with a hydrogen and a plus charge. Nothing on 3. Those famous 2 methyl groups that have done absolutely nothing this entire time on 4. And what you're going to see is on 5, we just have 2 OHs, and I'm going to drop this wedge because I only really need to show wedges for, chiral centers, things that are attached to 4 different things. But I'm not even attached to 4 different things because I have 2 OHs on the same carbon number 5. So no reason to keep that wedge if you're wondering where it went. Okay, and then just to get to the end, we just have to deprotonate, bring in good old water one more time, and you get our product. Okay, gang, that does it for the mechanism. Let's hit the synthesis problem and close the book on carbonyls, ketones, and aldehydes. Okay, gang, rounding out this worksheet, we have a synthesis problem where we need to make this right over here, our target molecule, with pieces of 4 carbons or less. So you know what the golden rule is. We always count our carbons, right? So we have 1, 2, 3, 4, 1, 2, 3, 4. So luckily we have a total of 8. So I think you all agree with me, unless we want to make our lives unnecessarily difficult, we're definitely going to be using 2 pieces of 4. Okay? So I hope what you're seeing is there's a double bond, and I hope that is triggering your Wittig sense. Okay? So this is a double bond. We can absolutely stick 2 4 carbon pieces together with a Wittig reaction, but remember we have to evaluate what kind of double bond we've been handed, because that will determine, do we need a yllid coming off a conjugated system, or can it just be a normal regular yllid? So if we take a look at this, right, we need to figure out if this is a Z or E double bond. So on this side of the double bond, we have the methyl versus this ethyl in terms of priority. It's definitely going to be this piece right here. And I think you can see on the other side, right, we just have this butyl piece, this piece right here. I'm bad at counting carbons, you know what I mean. This piece is definitely higher priority. This is the higher priority. So I think you can see this is a Z double bond, okay? So luckily this can just be a normal Wittig reaction. So feel free to pick how, there's no, one side or the other that's determining how we slice this up. And let me just double check what I did in the answer sheet so I don't do anything differently. Okay, yep. So what I did was I picked this piece right here to be the carbonyl. The secondary carbon right there became my carbonyl, which forced the other piece to be the yllid. Now, I'm going to go ahead and draw it like this at first. But remember, this can absolutely be represented as carbanion PPH3+. Okay? So now we need to, so arguably you could I don't know if you could stop here, right? There's carbons in the triphenyl thing we have going on. I'm going to show you how to take this back all the way to butane. I'm not saying you have to, I'm just saying I'm going to show you how to do it, right? So remember, let's do this piece, it'll be easy. We have to oxidize an alcohol to get this. We know that's how we can get an alcohol. I'm going to move this down for convenience. And then your jOeCHEM 1 kicks back in. Remember, we know we can get alcohols on our structures. We have to have a good leaving group. And remember, this is secondary, right? So we could do SN2 with NaOH, but in the secondary position, remember, we like to use an SN1 pathway. We like to throw in water. we know bromine would leave, the water would attack. Just dusting off some old knowledge. And then if you had to even do this, you could use Br2, light and heat. We know bromine would selectively be flocking to these secondary positions. Okay, now the yelid, right? It's a little bit more new chemistry. So remember, one of the last things you do is you throw in some type of base, whether it be T-butoxide, whether it be butyl lithium. I'll put or butyl lithium, or you could use LDA as well. Whatever you're more familiar with, feel free to use a wickedly strong base. Big, bulky, strong, that's what you're looking for. Remember, that's the last thing you would need to do to deprotonate this position, right? And that's how you get the lone pair over there, right? So we know before that, you just have PPH3 attached from a phosphorus SN2. So remember, we're gonna have to step this back. We know PPH3 needs to be there. And then you can have something like this, some type of good leaving group. You can use chlorine. I'm gonna use chlorine because we know how to get to that product. We can just use free radical chlorination, which we know will give us the most amount of primary alkyl halide, which sets us up for the SN2, which then sets us up for the deprotonation, which sets us up for the Vidig. Whew. All right, gang, so I'm hoping, especially after these two worksheets, you're feeling a little bit more comfortable with aldehydes and ketones. And if you're still not feeling that way, that's okay. This stuff is hard, but you're smart. So you just need to take some practice, organize your thoughts, organize everything you need to know, and just methodically work at it. And I promise you, you'll be speaking about this stuff just like you thought talking about Grignards and stuff like that, compared to when you started jOeCHEM, right? You're just like, how do I know this much more? It's just because you're methodically chipping away at it and learning the concepts. If you're watching this video, that means you've financially supported jOeCHEM, and I just want to say, hey, thanks. You're awesome. I hope this has been a very helpful tool to help you learn and conquer organic chemistry. I'm so happy you're using it now. I hope you're using it towards the end of your organic career, and no matter what, I hope to see you all in the next video.